You think you understand light, right? Flip on a lamp. The room lights up instantly. Clearly, light just moved. Simple, natural, nothing to question. But hold on for a second. Look straight at what everyone takes for granted. Light from the sun has to travel a staggering 150 million kilometers to reach your eyes. So what is actually making that colossal journey? You never ask yourself this, do you? That's fine. For 3 centuries, geniuses didn't ask either. From Huygens in the 17th century to Fresnel in the 19th, everyone believed light was a wave. A wave like when you throw a stone into a pond, ripples spread out. The water surface vibrates. And since waves always need something to travel through water, air, a guitar string, they invented something that sounded so reasonable it was hard to argue against: the ether, an invisible, weightless medium filling the entire universe, carrying light the way water carries ripples. That idea wasn't just popular, it was scientific gospel, taught in schools across Europe and America, considered more obvious than the sun rising in the east. And then in 1887, Michelson and Morley decided to test that belief. They didn't doubt the ether. They just wanted to measure how much light speed changed as Earth moved through that medium. Yet when light passed through the most precise instrument humanity had ever built at the time, they found nothing. A blow to intuition so powerful that all of classical physics staggered. And for me, that's the most beautiful moment, when something everyone was certain was true turned out to be completely wrong. And just as the ether began to crack, another figure stepped onto the stage and changed the entire game. James Clerk Maxwell. From 1861 to 1865, in an unbelievably short span of time, he wrote down a set of equations describing how electric and magnetic fields are tightly linked, chasing and transforming into each other, and how they can propagate through space on their own. No need for the mysterious medium humanity had spent centuries imagining. That idea at the time wasn't just new. It was almost a slap to intuition. How can something exist if it isn't matter? How can it spread without anything holding it up? But that's exactly what Maxwell proved. Light isn't an object racing through the universe. It is the coordinated oscillation of 2 invisible but immensely powerful entities, the electric field and the magnetic field. If you try to picture light as a stone being thrown, you're misunderstanding it from the start. Imagine it instead as a dance wave rhythm of electromagnetic fields, spreading without carrying any scrap of matter. A subtle, graceful change completely unlike anything your everyday intuition has ever encountered. Maxwell didn't just explain light. He ripped out by the roots the idea that everything real must have matter. And from that moment, physics began stepping into the age of fields things, invisible yet dictating how the entire universe operates. While the world was still struggling to grasp Maxwell's invisible fields, in 1905, a 26-year-old working in a patent office in Bern asked a simple but dangerous question that made all of physics stand up straight. If light always keeps the same speed, then what has to change? No one wanted to answer that, because if you really faced it, all the intuition you rely on to understand the world, everything from how you think about motion to the flow of time in your head, would collapse like a pile of wet paper. And Einstein, with the stubbornness typical of youth and an almost frightening sense for truth, didn't just ask the question. He marched straight into it as if it were the only path to reality. His answer, presented in the 1905 paper, hit classical physics, which had stood firm for over 2 centuries, like a punch. Space is not fixed. Time is not absolute. And if you move faster, time will run slower compared to someone at rest. Not in science fiction, not in philosophy, but in the very equations describing how the universe works. Imagine you sitting in a car going 100 miles per hour. In everyday intuition, if you turn on a flashlight pointing forward, you'd think the light would go 100 miles per hour faster than when you're standing still. But Einstein said, no, light will go at the same speed, no matter what you're doing. So what gives way to make that happen? Space, time, both bend, stretch, adjust just to keep light speed constant. It sounds like a joke, but it's what nature stubbornly enforces on us, and that's just the warm-up. When you approach the speed of light, something no car on I-95 or California freeway can do, but particles and accelerators do every day, your time begins to flow slower than everyone else's. Your clock ticks at a different rate. Your body, if it could survive at that speed, would age more slowly. This isn't abstract theory. It was straightforwardly confirmed in the 1940s when physicists discovered that muons, tiny fragments born from cosmic rays high in the atmosphere, should decay almost instantly. Yet they lived longer than normal when plunging toward Earth near the speed of light. They extended their lifetime not because of magic, but because their time truly slowed down. And length contraction? Oh, you might not notice it driving to the grocery store, but when you move fast enough, lengths in the direction of motion shorten. At jet speeds, the contraction is so tiny no one can measure it, but at 1% of the speed of light it becomes obvious. And for particles and accelerators forced to race in circles millions of times per second, length contraction is undeniable. If any of this makes you a little dizzy, good, that's the correct reaction. Einstein didn't break physics. He broke your intuition, and your intuition turned out to be wrong. Some people feel betrayed when they hear this. They want a solid, fixed universe running on rules they've known since kindergarten. Throw a ball and it goes faster if you run in the direction you throw. Turn on a light while moving, and the light should add your velocity. But nature doesn't care what you expect it to do. It just does what it does. And if keeping the speed of light constant means bending time and space, then that's what nature will do, whether you like it or not. The beautiful part is that everything Einstein said can be tested. The GPS you use every day to get to Starbucks or Costco only works because the satellite system constantly compensates for time dilation. Without relativistic corrections, your position would be off by miles after just a few minutes. We live in a world where every smartphone quietly admits Einstein was right. But all these strange things, time dilation, length contraction, space and time merging, lead to a deeper question. If the universe has to alter its own structure to keep light moving at one single speed, then what does light itself experience? What kind of world does it live in? With space and time bending out of the way for it, does its journey even mean anything? And to truly understand what light experiences, or rather, doesn't experience anything, we have to take one more step into the strange territory Einstein opened in 1905. We've talked about space and time bending to accommodate the speed of light, but now look straight at the main character of this story, the photon. The photon is a special case in nature. It has zero rest mass, something experiments from the early 20th century to today have found no deviation from. Precise measurements in quantum mechanics and astronomy, from Carl Jansky's 1931 radio wave observations to modern gamma-ray spectrum analysis, all confirm the photon has no mass. And because its mass is zero, it is forced to move at the speed of light, 299,748 ms, 790,748 ms, the number internationally fixed since 1983, when the speed of light itself was taken as the standard to define the meter. This isn't the photon's choice. It's the only condition under which it can exist. But here's what upends our worldview. If you're always moving at the speed of light, your proper time doesn't pass. You can picture this through what we actually measure in real experiments. From the 1940s, Bruno Rossi and D.B. Hall's group at MIT observed muons created at 15 kilometers altitude, particles that live only about 2 microseconds at rest, still reaching the ground before decaying. That can only happen if time for them slows down. The 1971 Hafele-Keating experiments, flying 2 atomic clocks around Earth on Boeing 707s, gave similar results. The airborne clocks ran slower than ground clocks. All this data says the same thing. As you approach the speed of light, time slows. And when you reach the speed of light like a photon, time stops completely. Not almost stops, not very slowly, but doesn't flow a straight line with no trace of moments. Try imagining this truth with a familiar example. Sunlight. From the sun's surface to Earth, the distance is about 149.6 million kilometers. We've learned since childhood that light takes roughly 8 minutes, 20 seconds to cover it. And that's completely true for us, for our clocks, for our hearts beating to our rhythm, for GPS satellites in orbit needing daily relativistic corrections. But for the photon that just left the sun's photosphere, that 150 million kilometer path happens in 0 seconds. No 8-minute journey, no on the way, no halfway there. In the photon's own timeline, the event of its emission and the event of it hitting your eye occur simultaneously. One end of the universe and the other end can be billions of light years apart, but for the photon, that distance is simply nothing. And to avoid misunderstanding, I want to stress what my students often get wrong the first time. Don't try to imagine you're flying along with the photon. Many people try and almost immediately hit a dead end. Why? Because the photon's perspective is a physically meaningless concept. No reference frame exists that moves at exactly the speed of light. All reference frames are for objects with mass. That is, for us, for electrons, for spaceships, for everything that can never reach that ultimate speed. Saying, time doesn't pass for a photon doesn't mean the photon feels it. Photons have no feelings. Photons have no clock. Photons have no experience. It doesn't live in a world where time is a flow. It doesn't divide time into before and after. It has no moments. It only has the relation between two events, emitted in one place and absorbed in another. Everything else, the journey, distance, speed, path only, has meaning in our reference frames. We creatures living in curved, slowly flowing space-time. For the photon, there is no in-between, no gradually approaching, no traveling across vast space. All of that is a product of human perception. And this is the part I always love telling students in class at Caltech. Light doesn't experience a journey, it simply appears when conditions are right. When an electron drops to a lower energy level and releases a photon, or when a molecule absorbs that photon and vibrates. Between those two events, there is no journey at all in the photon's world, only in yours. And if the story of the photon has started making your intuition wobble, brace yourself, because what comes next is like a scientific cold case whose outcome shattered humanity's entire worldview. We have to go back to 1887, a time when the theory was still seen as the bedrock of physics. No one seriously questioned it, not because they were lazy thinkers, but because every theory of light at the time, from Huygens, Fresnel, Young, all the way to Maxwell, simply assumed light needed a medium to propagate. The ether was the air of the universe, the water of light waves, the canvas on which nature painted every optical phenomenon. It wasn't just a hypothesis. The ether was the foundation of lectures, textbooks, and scientific thinking at the end of the 19th century. Our universe without ether seemed as bizarre as a ship with no sea to sail on. But that bedrock was about to be smashed by two men, Albert A. Michelson and Edward W. Morley. Michelson was an outstanding optical physicist, born in Prussia, but raised in America, who later became the first American to win the Nobel Prize in Physics in 1907. He wasn't a rebel against the ether. He believed it existed and just wanted to measure how Earth swam through it. Morley, a talented experimental chemist and physicist at Case Western Reserve University, joined Michelson in building an instrument that still makes young scientists look up in awe. The Michelson-Morley interferometer, one of the most precise devices ever constructed at the time. Their idea was simple but razor-sharp. If Earth orbits the Sun at about 30 kilometers/s, then when light travels in the direction of that motion, it should feel a stronger ether wind than when traveling perpendicular to it. This should produce a tiny difference in the time light travels along the two arms of the interferometer. Not much, just a fraction of a fringe shift was enough to confirm the ether's existence. Imagine standing on a boat and rowing with the current or across it. The speed you feel would differ. Michelson and Morley wanted to prove the same for light. No one thought they would fail. There was no reason to fail. Everything, every theory, every prediction said they would see a small shift. So they began measuring. In 1887 in Cleveland, Ohio, over many months, they rotated the interferometer in many directions, repeated the measurements hundreds of times, under many different conditions. No sloppiness, no good enough results. This was a serious investigation carried out by people who believed they were about to confirm a great truth. But the result was like a punch to the face of intuition. No change at all, no difference, no phase shift, no sign that light was affected by Earth's motion. The ether, if it existed, left absolutely no trace. You have to understand how shocking this was. Imagine investigating a crime where every piece of evidence points to one suspect, but when you open his door, the room is completely empty, not a single thing inside, not just a lack of evidence. The evidence of absence made every previous theory suspect. Michelson and Morley tried again, and again, and again. The result never changed. Zero. No heather wind in space. No slowing of light in the direction of Earth's motion. No heather sea for our planet to swim through. If you want to feel the tension of that moment, imagine me telling this story in a Caltech classroom. Two men built a wonderful instrument, measured a phenomenon they were certain must exist, and nature looked straight at them and said, no. And that wasn't a gentle no. It was a no that shook the foundations of physics. Why? Because only two possibilities remained. One, Michelson and Morley were wrong. Their instrument was wrong. Their method was wrong. Yet their interferometer was so sophisticated that every scientist respected it. And follow-up experiments in Germany, Italy, America, Japan, over decades, all repeated the result. Zero. The chance of a major error persisting across so many independent experiments is virtually nil. So only the second possibility remained. The ether does not exist. There is no medium carrying light, no mysterious substrate the whole world had taken for granted. An idea that had existed for over 200 years, taught everywhere, built into every optical theory, turned out to be wrong, completely wrong, and history, with all its cruelty, chose the second answer. This was the moment 19th century physics collapsed like a building whose single supporting column was removed. But that very moment also cleared the way for a 26-year-old named Einstein to step in and say, maybe the problem isn't with light. Maybe the problem is with how we understand space and time. You can see how all the pieces start talking to each other. Ether vanishes. Light speed doesn't change. Time and space begin to bend. And the photon lives in a timeless world. None of this is disconnected stories. They are fragments of the same great mystery. And the Michelson-Morley experiment was the opening shot of that revolution, a simple experiment that found nothing, yet demolished an entire empire of human thought. Funny, but also beautiful. Sometimes in science, finding nothing is the most important discovery of all. When the ether was finally pushed off the stage, when Michelson-Morley left us with a huge void that no one knew what to fill it with, we were forced to go back to a seemingly simple question. If light doesn't need a medium to travel, then what exactly is moving here? This is when a strange but breathtakingly beautiful truth steps forward. Light is not a stream of particles flying at high speed, nor is it a mass of matter being pushed in the traditional way. Light is a pattern of self-sustaining oscillation, pattern woven from electric and magnetic fields chasing each other through space. Imagine two invisible entities, one called the electric field, the other called the magnetic field. Neither has shape, neither has color. You can't photograph them, and you can't put them in a box. But when the electric field changes, it summons a magnetic field. And when the magnetic field changes, it creates a new electric field. On and on. These two invisible entities generate each other, propagate themselves through space, like a pair of dancers entwined in an endless tango. The electric field pushes the magnetic field one beat. The magnetic field pushes the electric field one beat. Beat after beat, it spreads outward forever, and that spreading is what we call light. No electron is thrown forward. No molecule is dragged along. No matter leaves point A to go to point B. Only the pattern, a changing value pattern in space, is propelled by its own change, without carrying a single scrap of matter. If this feels a bit strange to you, compare it to more familiar waves you've encountered in life. Take a simple example, water waves. When you throw a stone into a pond, ripples spread out, but the water doesn't move from the center to the edge. The water molecules only oscillate up and down. It's the pattern, the circular ripple shape that travels, or sound waves. When you speak, your vocal cords make the air vibrate. The air doesn't rush straight to someone else's ear. No molecule of yours flies onto their face. Only the pressure, change the oscillating pattern moves. The water doesn't go. The air doesn't go. Only the pattern goes. And light is the same, except that light doesn't need any medium to carry that pattern. It doesn't need water, like water waves. It doesn't need air, like sound waves. It doesn't even need a vacuum to be something. It only needs space. Completely empty space is enough. This is what makes light one of the strangest creations nature ever came up with. Nature says, I don't need particles, I don't need a substrate. I just need electric and magnetic fields, and they will push each other across the universe. If you want to picture this more clearly, try imagining an auditorium where people pass a motion to one another. The first person leans right, the next leans right after them, then the next. No one runs from the front of the room to the back. No one leaves their spot, but the motion travels from the first row to the last. That's exactly what light is, except at 300,000 kilometers per second. When you see water waves spreading, you're seeing matter oscillating in a medium. When you hear a car horn, you're hearing air being compressed and rarefied. But when you see light, you're seeing a pure pattern moving without carrying any material particles. Not a single electron leaves the light source and crowds its way to your eye. Not a single molecule is pushed along by the light. Light is unlike any wave you've ever encountered before, and humanity's first mistake was trying to force it into familiar sensory models. But nature doesn't care what's familiar to human senses. Nature likes to play by its own rules, and light is the first proof you meet in life. It behaves like a message without a messenger, a dance without a stage, a transformation without a foundation, something that propagates without anything truly going, and this paradox is the starting point for understanding every strange thing that follows in quantum mechanics. Because once you accept that light is not a stream of particles, nor the movement of matter, but only a pattern of self-sustaining change, you'll be ready to face the even more terrifying story. That pattern sometimes behaves like a particle, sometimes like a wave, sometimes like both, sometimes like neither. But before we get to those paradoxes, you have to swallow this simple yet uncomfortable truth. Whole, light doesn't carry anything. It doesn't push any particles. It is only a propagated change. And that propagation is what we call by a name so familiar, no one questions it. Light. And just when we start getting comfortable with the idea that light is only a delicate pattern of electric and magnetic fields, a purely immaterial dance, nature decides to throw the first big twist of the 20th century. If you think light is already weird, wait until you meet what late 19th century physicists called the photoelectric effect. The story begins in 1887, when Heinrich Hertz, the first person to generate and detect radio waves, accidentally noticed something strange when he shone ultraviolet light onto a metal plate. Electrons were knocked out. Yes, light, something we thought was just a pattern, could knock electrons out of metal. Hertz noted the phenomenon quite calmly, as if he just picked up a strange stone on the road, but he didn't dig deeper into it. It wasn't until more than a decade later, in 1902, that a scientist named Philip Leonard conducted a much more detailed series of experiments. And what he found started shaking the entire wave theory of light like a wooden house in a storm. Leonard observed that when light is shone on metal, the brightness, intensity of the light doesn't determine whether electrons are knocked out strongly or weakly. What matters is the color of the light, or in physics terms, its frequency. Blue or violet light, high frequency, can knock electrons out with high energy. But red light, even if you increase its brightness dozens of times, still can't knock out a single electron. This was completely illogical under the wave model of the time. In familiar intuition, a stronger wave should push things harder. A bigger wave should slap electrons farther. But nature didn't care about human intuition at all. The intensity of light only increases the number of electrons knocked out, not the energy per electron. And worse, if the frequency is below a certain threshold, you can shine light so bright it blinds the room, and the electrons still won't budge. This wasn't an experimental error. Leonard did it hundreds of times with different metals, sodium, potassium, cesium, and the results were always the same. A huge brick dropped right on the head of every wave theory at the time. Why does frequency matter, but intensity doesn't? In 1905, a patent office clerk in Bern named Albert Einstein decided to step in. Decided is too mild a word. Einstein jumped into this problem like someone who sees a loose thread in the shirt the whole world is wearing and knows that if he pulls hard, everything will unravel. He proposed a bold idea that even the most brilliant physicists of the day found hard to breathe. Light is not just a wave. It also comes in discrete packets of energy, later called photons. According to Einstein, the intensity of light is like the number of bullets fired. But the power of each bullet depends on the color, not the number. Red light can fire millions of low-energy bullets, but none strong enough to knock an electron out of metal. Blue light fires fewer bullets, but they're strong enough to kick electrons out instantly. This explained perfectly everything Hertz and Leonard had observed, and to make it more convincing, in 1916, physicist Robert Millikan, who spent years trying to prove Einstein wrong, ended up providing the most convincing evidence that Einstein was right. Millikan didn't want to admit it, but the data didn't care who it flattered. The slope of the graph of electron energy versus light frequency matched Einstein's model perfectly. No more debate needed. Nature had decided. And thanks to that beautiful explanation, Einstein received the 1921 Nobel Prize in Physics. Not for relativity, as many think, but precisely for the photoelectric effect and the idea of the photon. Pause for a moment to grasp this cosmic twist. For hundreds of years, light was considered a wave. Then Maxwell came and solidified it with electromagnetic theory. Everything was fine. Everyone was happy. Then Hertz saw electrons knocked out. Leonard saw color mattered more than intensity. Einstein said, yeah, because light comes as particles. And suddenly, what we thought we understood became more mysterious than ever. What is light? Wave? Particle? Both? Neither? Einstein only said it comes in packets of energy. But if you think this made everything clearer, sorry. You're about to step into the territory where light behaves as if it has two personalities at once. One cooperative when you're not looking, and a completely different one when you try to observe it. But don't rush ahead. In this part, you just need to grasp one thing. Light began to have particle properties, and that's when physics realized it had only opened the first door into a gigantic maze. If you think the idea that photons are particles is just a theoretical joke Einstein made up to explain a few troublesome photoelectric experiments, let me take you to the late 20th and early 21st centuries, where labs around the world started firing one photon at a time, like tossing individual marbles into the universe, and listening to how it responds. This is no longer a metaphor. This is fact. From the 1970s to the early 2000s, ultra-sensitive detectors like photomultiplier tubes, avalanche diodes, and later superconducting devices at near absolute zero temperatures allowed us to see light at the smallest possible level. Single photons. Experiments by groups like Kimball, Degenis, Mundell at Caltech, Grungy, Roger Aspect, and Orsay, and modern ones at MIT and NIST all showed one thing that theory had said since 1905, but took humanity nearly 80 years to truly hear with our own ears. Light doesn't arrive as a smooth flow. It arrives as individual knocks, individual hits, individual discrete events. When you dim a light source to an extremely low level, so low it emits only one photon every few microseconds, the detector makes a tiny click for each photon. No steady hiss like rain, no whoosh like flowing water. Just click, click, click. Each click is a photon, an event. If light were truly a continuous wave, the detector would never produce such jerky sounds. But at intensities so low, you're certain there can only be one photon on its way to the detector. What you hear is like someone's footsteps on a wooden floor in a quiet house at midnight, separate, distinct, unmistakable. And this isn't some special measurement reserved for big labs. Today, single photon experiments are foundational to quantum information technology. At the University of Vienna, Anton Zeilinger 2022 Nobel laureate used individual photons to achieve the first quantum teleportation in 1997. At NIST, single photons are used to measure subtle properties of cold atoms. At IBM and Google, qubit experiments also use these discrete photons. All confirm the same truth. Light doesn't come in a stream. It comes in individual hits, like tiny energy bullets. And if you want to experience the feeling of hearing light, watch a photon counter in action. In many publicly available experiment videos, people turn on an ultra-weak laser, or even better, a single photon source created via SPDC, spontaneous parametric down conversion in nonlinear crystals like BBO. Then they direct the photons to the detector. You see a black screen. You hear silence. Then click. One photon just hit the device. Then click again. If you double the brightness, you don't make the photons stronger. You just make them arrive more frequently. But each photon still produces only one event, one single click. There's no such thing as one photon splitting its energy and making two smaller clicks. Each photon arrives with its own energy. This happens at every wavelength, from feeble red light at 650 nanometers to high-energy photons in the ultraviolet or gamma range. In every case, the detector never records half a photon or part of a photon. You either have a photon or you don't. No in-between state. This is extremely important because it directly confirms Einstein's idea. Light energy arrives in discrete packets that cannot be subdivided. And if you want an extremely convincing example, look at HBT experiments, where light from stars is analyzed for how it correlates. Stars shine like billions of atoms firing photons randomly. And even in that sophisticated case, photons still appear as discrete events, not a continuous flow. This is no longer theory. This is the universe speaking in clicks. And if light arrives like that, you'd think, okay, light is particles, so it behaves like quantum bullets. But no, this is the part that makes first-year students cry. Even though photons arrive one by one, if you let them pass freely through two slits, they create an interference pattern like waves, a beautiful paradox that forces you to admit nature as both more elegant and more mischievous than any model humans have ever invented. One photon at a time, one click at a time. And then suddenly, when you collect enough clicks, you see alternating bright and dark bands. The interference pattern, the unmistakable signature of a wave. A particle cannot interfere with itself unless it does. And that's the story of part 9, where the strangeness of light doesn't just double, it multiplies infinitely. Even though light arrives as individual tiny energy bullets, it still behaves like a wave when you're not looking at it. Nature smiles again and says, you still don't understand anything. You think the photon is a particle? Just wait until you see how it goes through two slits at the same time. And here, right from the point where the photon starts clicking one by one into the detector, we step straight into the strangest experiment in the entire history of science, one that didn't just change physics but changed the way we understand reality itself, the double slit experiment. The story begins in 1801 when Thomas Young, a British physician and physicist, stood in a darkened room and shone light through two narrow slits. When light passed through one slit, he got a smooth, bright band on the screen. When it passed through the other slit, he got a similar bright band. But when both slits were open, he didn't see two bright bands overlapping as an ordinary person would expect. Instead, he saw an alternating pattern of bright and dark stripes, like interfering water waves, a clear sign that light behaves like a wave. Young's result was one of the hardest blows to Newton's particle theory of light and reinforced the belief that light is a wave. But Young lived before Maxwell, before Einstein, before the photon. He had no idea that the experiment he performed would become one of the most important fuses for quantum mechanics more than a century later. Now, jump to the 20th century, when technology was sophisticated enough that we could not only shine light through two slits, but also fire individual photons, one discrete packet of energy at a time through a double slit. If the photon really is a particle, as Einstein suggested in the photoelectric effect, You'd expect them to leave two bright bands, one for each slit, just like shooting marbles through two narrow gates. But no, when you fire photons one by one through two slits, you get the exact same interference pattern Young saw. This is no longer continuous light. These are individual photons, tiny energy bullets, yet when you collect enough of them, the screen behind shows alternating bright and dark fringes. The undeniable signature of a wave. Imagine firing bullets one by one through two slits and eventually discovering that the positions where the bullets land form a wave pattern. This makes no sense in the classical world, but it's an obvious fact in the quantum world. And even stranger, you don't need to fire many photons at once. You can space each photon a few microseconds or milliseconds apart, far enough that they cannot interact with each other. Yet even then, they still produce an interference pattern as if they know both slits are open and interfere with themselves. From the 1960s onward, a series of experiments by physicists like Jeffrey Taylor, 1909, with ultra-low light intensity, Helmut Rauch, neutron interferometry, 1974, and Alan Aspect, 1980s, extended this experiment to every kind of particle, photons, electrons, neutrons, even C60 molecules, fullerenes, thousands of times heavier than a photon, also produce interference when passing through two slits. The universe seems to say, if something can exist as a wave, it will. But the madness of the double-slit experiment doesn't stop there. If you place a detecting device right at the two slits, a super-sensitive detector, to see whether the photon goes through the left slit or the right slit, what happens? You'd think the interference pattern would stay the same because a photon is still a photon. But no, when you observe the path, when you simply want to know which slit the photon went through, the interference pattern disappears instantly. The screen behind no longer shows bright and dark fringes. Instead, it displays two blurry, bright bands, as you'd expect from particles going through two slits. No interference, no wave, as if the photon suddenly changes personality just because you looked at it. This is not exaggeration, not a metaphor. These are results repeated in countless labs around the world for over a century. And this is exactly what makes physics students bang their heads on the table. The photon behaves like a wave when you're not looking, but like a particle when you are looking at it. I often tell students this line so they remember it forever. It knows you're watching. Of course, the photon has no consciousness. It has no eyes, no brain, no ability to know anything. But the mathematical system describing it, the wave function, changes instantly when we measure. That change collapses the quantum superposition and forces the photon's behavior to switch from waveform to particle form. And the strangeness doesn't end there. In 1978, John Wheeler proposed the delayed choice experiment. The slit the photon goes through can be decided after the photon has already passed through the slits. Yet the result still changes, as if the photon knew in advance what you were going to do. No classical phenomenon is like this. You can't throw a stone through two doors and then midway decide which door it should have gone through and expect the outcome to change. But with the photon, it does happen. The only explanation quantum mechanics accepts is, before you measure, the photon does not go through the left slit or the right slit. Those questions have no meaning. The photon exists in a superposition of possibilities, and when you measure, you force the system to choose one specific outcome. And it's that act of measurement, not the intrinsic nature of the photon, that makes the interference pattern disappear. This is the point I want you to feel deeply. The double-slit experiment doesn't just teach us about light. It teaches us that reality is not what we think it is. Classical intuition, the idea that particles have clear, definite, independent paths, regardless of whether we observe them, dies right here. And if a photon can go through both slits at once when we're not looking, but only through one when we are looking, then going through where is not a real property of the photon. It's only the answer nature gives to the question you force it to answer. The double-slit experiment shatters every illusion we have about the microscopic world. It doesn't just say light is a wave. It doesn't just say light is a particle. It says light is something human language was never prepared to describe. And the most beautiful part, if you ask me, is that this experiment remains as strange today as it was in 1801, when Thomas Young stood in front of a small slit of light in a dark room in London and accidentally opened the door to a universe where existence is not particle or wave, but something completely different. So why does merely observing change the photon's behavior? If you've already seen the photon interfere with itself when no one is looking, but behave like an obedient particle when we decide to see which slit it goes through, then you've touched the heart of the quantum problem in this world. The act of observation is not passive, it is a physical interaction. When you place a detector in the slit, you're not just looking for fun. You're forcing the photon to interact with a device, with the environment, with another physical system. And those interactions do what quantum physics calls collapsing. The superposition coherence is lost, and the system is forced to choose one of the possibilities it previously held simultaneously. Imagine asking the photon, "Hey, which slit did you go through?" Nature looks at you, shrugs, and says, "If you want to know, I'll pick one of the two, but you'll have to give up the interference pattern." Why? Because to know which slit the photon went through, you must create an interaction strong enough to leave a trace. That trace prevents the photon from spreading across both possibilities anymore. You've destroyed the ability to exist in multiple states at once, an ability that is the foundation of quantum mechanics. That's why I often joke, nature doesn't like being asked, "What are you doing?" It doesn't answer that question without changing itself. This isn't just in lectures or textbooks. It's been confirmed in countless experiments from the 1920s to today. Niels Bohr and Werner Heisenberg called this the principle of complementarity. You cannot ask about particle and wave properties at the same time. I call the double slit experiment with a detector the central mystery of quantum mechanics. But there's more. The 20th century still had one twist for us that still makes many physicists pause and thought even today. John Wheeler's delayed choice experiment, proposed in 1978. Wheeler asked a question that gives people chills. What happens if we decide to observe the photon after it has already passed through the two slits? It sounds like a paradoxical joke, but Wheeler really proposed ways to do this. With Mach-Zehnder interferometers stretched over tens of meters, or even with light from galaxies billions of light years away. His idea was simple yet horrifying. Let the photon go through the system as if both slits are open. Then, right before the photon hits the final detector, you decide whether to merge the two paths to create interference or separate them to see the path. And what stunned the world is, the measurement outcome depends on that final choice, even though the photon seems to have already completed its journey. If you choose see the path, the photon behaves like a particle. If you choose see interference, the photon behaves like a wave, as if the photon waits for your decision and then redecides how it should behave. Wheeler once said, "It's not that light decides the past, it's that your measurement decides how we can speak about light as if it had a past." And this is the point that makes any newcomer to quantum physics want to stand up and run. In quantum mechanics, the question you ask determines the answer nature is allowed to give you. There is no real path independent of the measurement behavior. There is no real outcome before you create the context to measure it. Nature doesn't care what you want to know. It only tells you what the quantum structure of the measurement forces it to answer. Remember this. The photon doesn't change its attitude because it likes to toy with you. It changes because you created a physical interaction when trying to measure the path. In the quantum world, interaction means change. There is no neutral measurement, no distant observation without influence. Every measurement is a push, a touch, a disturbance to the system. The more you try to know, the more you make the system change. And when you choose different ways to measure, you are literally choosing different realities that nature can manifest. This isn't vague philosophy. This is what every lab from Orsay to MIT, from NIST to Vienna has confirmed with clear data. In other words, you don't break the universe when you observe it. You only reveal one of the many faces the universe can show. And light, with its stubbornness, mischief, and complete disregard for human intuition, is the perfect example of that. It shows you asking the wrong question is the fastest way to make nature change its answer. And when you ask, which slit did you go through? Nature smiles and replies, if you force me to answer, I'll pick just one. But don't blame me when you no longer see the interference. After all the shocks that the double slit experiment, the photoelectric effect, and delayed choice have thrown at us in waves, you might think the most reasonable conclusion is, okay, light is both a wave and a particle. But let me say straight out what it took physicists nearly a century to dare admit. Both descriptions are wrong. We only use the words wave and particle because those are the two kinds of behavior human senses are familiar with. Waves spread out, interfere, soft like water ripples. Particles are discrete, definite, like marbles rolling on the floor. But nature has no obligation to resemble things you've seen before, and light taught that lesson by mercilessly smashing both models. Look back at history, when Newton said light is particles at the end of the 17th century. He was right according to the physical intuition of the time. Light travels straight, reflects, refracts like the flight of tiny bullets. But then in 1801, Thomas Young showed light interferes an unmistakable sign of waves. Newton's particle theory took a crushing blow. Then in the 19th century, Fresnel, Fraunhofer, Maxwell all reinforced the wave model until it became near absolute belief. No one had reason to doubt until 1905, when Einstein toppled that belief with the photon discrete energy packets that perfectly explained the photoelectric effect, which the wave model was completely helpless against. And so began a bizarre century where people were forced to say two sentences that sound like self-slaps. Light is a wave. Light is a particle. But when you try to understand light more deeply, you see both statements are crude simplifications of nature. It's not just photons that behave this way. Electrons, the tiny things that make up every atom, also produce interference when passing through two slits. In 1927, Davison and Germer's experiment at Bell Labs showed electrons scatter in a diffraction pattern just like X-rays. Then in 1961, Koch-Johnson did the double slit experiment with electrons and again got a wave interference pattern. But if you attach a detector to see which slit the electron goes through, measure its path, and then look at the result, the interference pattern vanishes, and the electron behaves like a particle. And the problem doesn't stop there. Neutrons, protons, helium atoms, even C60 molecules, molecular footballs made of 60 carbon atoms also interfere. In 1999, Marcus Arndt and Anton Zeilinger sent C60 through a grating and got an interference pattern. A molecule thousands of times heavier than a photon, nanometers in size, still behaves like a wave. If you try to force the particle model onto these results, you have to imagine the particle splitting itself, duplicating itself, then interfering with itself. Sounds completely unreasonable, but if you try to force the wave model, you have to imagine an electron with mass and charge spreading across all space like a lake surface. Also completely unreasonable. And this is why I say both words, wave and particle, are wrong. They are just desperate human attempts to describe something outside everyday experience. We have water waves, sound waves, classical electromagnetic waves. We have marbles, stones, classical imagined electrons. But nature never promised those familiar structures are enough to describe entities at the most fundamental level of the universe. When you say the photon is a wave, you're drawing a familiar but wrong picture. When you say the photon is a particle, you're drawing another familiar but equally wrong picture. Both are correct only in a very limited sense, and they fail completely if you force them to describe the full quantum behavior. And this is what matters. Our language, our vocabulary is too crude. It was built to describe human scale sizes, human scale speeds, human experiences. But the microscopic world doesn't care. Nature doesn't know what particle or wave means. It only knows its own quantum rules. And in those rules, an entity like the photon has no classical shape, no classical trajectory, no classical state. It exists as a wave function, a mathematical function that describes all the possibilities where it might appear, all the paths it might take. Not a wave in water, not a sound wave. A pure mathematical form living in the abstract space of probability, and the beauty and the pain of physics lie here. The wave function is not a visual image you can imagine, like a vibrating string or spreading ripples. It is a mathematical tool that tells you if you measure the photon, it's highly likely to appear here. If you measure differently, the outcome could be there. When you say light is a wave or a particle, you're describing measurement outcomes, not the true nature of light. One appears when you're not looking. The other appears when you are looking. Nature doesn't change what it is. It only changes what it allows you to see. This is hard to swallow, I know. Even Einstein once said, "This is what keeps me awake." But this is the necessary step before we abandon the two words wave and particle entirely and accept that nature operates with something completely different. The wave function describing possibilities rather than matter, and only becoming reality when you measure it. As soon as you remove the two distorted lenses called wave and particle, you can finally look straight at what nature actually uses to describe light, and not just light, but the entire microscopic universe, the wave function. But let me be clear, the wave function is not a real wave, not something you see with your eyes, and certainly not a visual image the human brain was built to understand. The wave function is a mathematical structure living in Hilbert space, which already sounds uncomfortable enough, but it is precisely what encodes all the possibilities a quantum system can exhibit. It doesn't tell you what the photon is doing. It tells you what the photon can do, and the probability that you'll see that outcome. And the funniest part is, in over 100 years of quantum physics, no one, not even those who wrote its equations, has ever seen the wave function. Schrödinger in 1926 called it a wave. Born in 1926 corrected him and said, "No, it's not a wave, it's probability." Both were partly right, and both wrong if you try to picture it with classical intuition. Look at the double slit experiment. If you don't place a detector, the photon's wave function spreads through both slits, not like a cloud of matter, but like a probability, a map of possibilities. It says the photon could appear here, could take this path, could take that path. But when the photon hits the screen, you see only one single bright spot, just one possibility selected. When you repeat the experiment thousands of times, those individual bright spots seemingly chaotic start, forming a perfect interference pattern. Beautiful enough that you have to admit something is calculating behind the scenes, and that something is the wave function. Another example, the electron in a hydrogen atom does not orbit the nucleus like planets around the sun. If you believe that picture, I'm sorry, it's completely wrong. The electron exists as a wave function surrounding the nucleus, and the orbital cloud images you see in textbooks are just probability maps. The electron doesn't run, it doesn't orbit, it isn't at a specific position before you measure. When you measure, you force the wave function to choose a position, and the electron appears there. In 1995-2000, experiments on beryllium ions and electric traps at NIST showed superposition disappearing instantly when the system interacts with the environment, even extremely lightly. This shows the wave function is not a real wave. This is possibility. And possibility is destroyed merely by the environment knowing some information about the system. When you ask nature, which path did it really take? Nature doesn't answer directly. It answers with probabilities. Nature doesn't tell stories. Nature doesn't explain process. It only gives outcomes. If you want to see an even bigger example, look at the 1999 experiments on C60 molecules by Marcus Arndt and Anton Zeilinger's group. A molecule of 60 carbon atoms heavier than a photon by 10,000 times still produces interference, meaning the wave function of an entire large molecule can spread like a probability wave. But when you measure the molecule's position, boom, it appears at a single point. No splitting, no blur. 1 point. The wave function says it could be in many places. The measurement says, no, now it's only here. And that is the special relationship between us and nature. We never see the wave function directly. We only see the answers that measurement forces the wave function to give. This isn't philosophy. This is what every experiment from 1920 to 2012 has confirmed. From Mach-Zehnder interferometers, neutron interferometers, to modern quantum computers with superconducting qubits at 10 millikelvin, all deliver the same message. Nature speaks in probabilities, not in pictures. When you demand pictures, you're forcing nature to use a language that isn't its own. And nature doesn't oblige you. If you ask, which path did the photon really take? The wave function says, there is no path, only possibilities. If you ask, where was the electron before I measured? The wave function says, nowhere or everywhere at once, depending on how you want to phrase it. And if you ask, so what's really happening between the moment the photon leaves the source and the moment it hits the screen? Nature replies, you're asking the wrong question. And this is what I want you to feel deeply. The wave function doesn't describe a process. It describes possibilities. It doesn't show you behind the scenes. It only shows you the final outcome every time you pull back the curtain. And if you feel like we still don't know what light really is, then congratulations, you're on the right track. When I started wrestling with quantum mechanics in the late 1940s, I had absolutely no intention of inventing a new way of looking at nature. I was just a young guy at Princeton who was fed up with tangled equations and wanted something more intuitive. I hated the vagueness, hated rules written like religious rituals, and I always believed that if nature does something, there must be a simple description I could explain to myself at 3 in the morning in my dorm room. Then I accidentally stumbled onto an idea that changed my whole life. The photon doesn't follow one path. It follows every path the universe allows. The idea didn't come in a flash of lightning. It grew out of frustration. At the time, everyone was using wave mechanics to describe electrons and photons' Schrödinger equations, oscillating wave functions. It was all mathematically beautiful. But I couldn't stand that no one could explain to me what's really happening. I needed a description. I could picture a physical story, not a mess of symbols. In a work session in 1947 at Cornell, while I was leaning back in a creaky wooden chair in my office, I realized no one forces the photon to follow a single path. Humans are used to seeing light go straight, so they assume it has to pick the straight path. But nature never signed a contract with us on that. Nature isn't bound by the intuition we inherited from throwing stones into ponds or watching marbles roll on the floor. So I asked myself, what happens if I let the photon take every possible path between points A and B? Every path straight, curved, zigzag, snaking like a serpent, even looping up to the moon and back, all of them. At first the idea sounded like a joke, but I wrote it down, scribbled on paper, then added little arrows, representing amplitude, a quantum quantity describing the contribution of each path. Each path gets its own arrow. When I rotated the arrows according to the mathematical rules, they added up. If 2 possible paths brought the photon to B with arrows pointing in the same direction, they reinforced each other. If they were out of phase, they canceled each other. I did this for hours all night. And the strange thing was that when I added up all the paths, every imaginable path I could draw, I found that most of the arrows completely canceled each other out. The wiggly paths had amplitudes pointing every which way. The weirdly curved ones, too. The longer paths had amplitudes that spun around many times and erased themselves. But one group of paths, the ones closest to the straight line, what classical language calls near the path of minimal time, had arrows pointing nearly the same way. They added up, reinforced each other, creating the largest amplitude. The final result looked exactly like what classical physics had always said. Light travels in a straight line, not because it really chooses the straight line, but because when you add every path, only the near straight ones don't get canceled. This was no longer intuition. This was mathematics. A kind of mathematics that let me understand what had previously only been taught as the law of reflection or the law of refraction. Snell's experiment, Fresnel, Maxwell, all fell into place. Light reflects with angle of incidence equal to angle of reflection, because adding every path gives that result. Light refracts when going from air to water, because the path with minimal time wins after summing all paths. Even Fermat's principle, light takes the path of least time, is just a consequence of adding quantum arrows. This wasn't a theory I tried to force. I just followed the math where it led. After I presented the idea at the Shelter Island Conference in 1947, one of the most important physics conferences of the 20th century, with people like Oppenheimer, Teller, Beatty, Schwingert, I saw physicists start to pay attention. Some thought I was crazy. Some thought the idea was too simple to be right. But what excited me most was that my path-summing method solved problems that other techniques struggled with, especially in quantum electrodynamics, where corrections like the Lamb shift or the anomalous magnetic moment of the electron required precision up to 10, 12. Every number matched. Not just matched, but matched so beautifully that I laughed out loud alone in my office when I calculated the results. When the wiggly paths, curved paths, wavy paths, absurd paths were all computed and cancelled exactly as they should, I knew I had touched a more honest part of reality. Not the human-favored version, not the intuitively expected version, but nature's own version. If you want to picture this, imagine the universe as a huge crowded gathering of countless paths. Each path is a participant reaching out, holding a little arrow. Most arrows point randomly up, down, left, right, and when you add them all, they cancel. But the group standing near one straight line hold arrows almost in the same direction. The agreeing crowd wins over the chaotic crowd. You don't see the entire process in the experiment. You only see the final agreement. That's light going straight. But light never chose the straight path. It listened to every path. And the straight path is the final result after every path is spoken. I love this idea, not just because it explained the data, but because it gave truth back to nature. Nature isn't simple. It's richer, weirder, vaster than any model we've ever tried to force it into. If you still feel shocked hearing that the photon takes every path at once, good, that's a sign you're understanding the true spirit of quantum physics. Because nature doesn't care if you want it simple. It only cares about truth. And the truth is, light doesn't follow one single path. Light tries every path. The result you see is just a summary nature gives after considering infinite possibilities. If it tries every path, why do we only see light going straight? What looks as simple as a flashlight beam is actually the final outcome of a vast quantum process where infinite paths compete and then cancel each other out. In the path integral, each path is assigned an arrow, an amplitude. These arrows have direction. The direction depends on the action of the path. If you change the path a little and the action changes a lot, the arrow spins hard and easily cancels with others. If changing the path only makes the action change very little, the arrow stays almost in the same direction. This is the key to understanding why light looks like it goes straight. Imagine adding millions of little arrows when directions scatter randomly. Their sum is almost zero, like a crowd of 100 people each pointing in a different direction. But if a group points nearly the same way, that combined sum makes a big, clear arrow. In the world of paths, the wiggly, roundabout, wavy paths make amplitudes spin wildly and self-cancel. Only one very special group of paths, the ones closest to the straight line, where the action changes the least have in phase arrows. They add up. They win. When you observe, you don't see the cosmic cancellation process silently happening. You only see the final result. Light goes straight. This explains all of classical optics. Take the law of reflection. Angle of incidence equals angle of reflection. Why not some other angle? Because if the photon tries every path from source to observation point on the mirror, all the weird paths self-cancel. Only the paths near satisfying minimal travel time, for Fermat, have in-phase amplitudes. When you add them, the stable path is the classical reflected path. Nature doesn't choose the reflection angle. It eliminates infinite other angles by cancellation. Snell's law of refraction is the same. When light goes from air to water, the paths with least action change are the bent ones. It's not that light likes to bend. All non-bending paths cancel each other, leaving only the configuration with the strongest total amplitude. When I first saw this in my calculations at Cornell in the late 1940s, it felt very strange. Every optics rule we learned as kids wasn't an imposed law, but just the surviving remnant of a quantum cancellation process. No special force needed, no intelligence from the photon, just mathematics, many paths cancel, a few win. The path integral also explains why light follows optical fibers. If you think light chooses the shortest path, you won't understand this. But if you let the photon try every path inside the fiber, even paths that bounce off the walls repeatedly, you'll see only the paths that maintain stable phase along the fiber add up. Paths that escape cancel immediately. So light, obediently, follows the fiber, not because it knows the way, but because every other path fails in the sum. This happens in other systems too. Electrons in solids try countless paths through the crystal lattice, but only paths with stable phase survive. That's the foundation of band structure, which makes transistors and computer chips work. It's not just photons that obey this principle. Every quantum object is governed by the cancellation and reinforcement of infinite possibilities. The philosophical part is here. What you see is the filtered version of reality. You never see the full chaotic mess underneath. Nature tries infinite paths, infinite possibilities, then self-destructs everything unstable. You only get the final music after the universe has edited out every wrong note. When we say light goes straight, we're describing the most stripped-down version of a monumental story. It's like looking at a calm river without seeing the millions of tiny water streams swirling, colliding, canceling, then merging into one single flow. The straight path you see isn't the primal truth. It's the winning result. That's the real beauty of light. The simple thing you see is the survivor after nature has eliminated every unfit choice. Sooner or later, after hearing about photons taking every path, wave functions spreading across space, and interference patterns disappearing when you observe, you'll ask the question almost every student I've ever met asks, so what does light do when no one is looking? The short answer is, the question has no meaning in physics. I'm not saying it's stupid. I'm saying it can't be defined in nature's language. Niels Bohr said this back in the 1920s. Quantum reality is not something that exists independently of measurement. It is something you can say about the results of measurement. Werner Heisenberg went further in 1927 when he wrote that the path of the electron is not something that exists before measurement. It is created by the measurement. That's the foundation of the Copenhagen interpretation, the dominant way of understanding quantum mechanics for many decades. I don't fully agree with every nuance of Copenhagen, but I agree with one thing. If you ask the wrong question, you won't like the answer. Asking what does the photon do when we're not observing is like asking what does the color blue smell like. The question sounds grammatically English enough to be a sentence, but it has no physical meaning. Nature doesn't keep a real path in a notebook waiting for you to open it. In the language of the path integral, the photon has no what it does in its free time. It only has the collection of all possibilities, and the wave function encodes them. When you measure, you force the system to give one outcome collapse. When you don't measure, there is no story happening in space, so the photon goes from this position to that position. If you beg nature to tell you the secret adventure of the photon between A and B, nature shrugs and says, I don't have that record. An easy example is Wheeler's delayed choice experiment. In that experiment, the decision to insert or not insert the beam splitter is made after the photon has passed the slits. The result still changes exactly as if the photon waited for you to decide whether you want to see wave or particle behavior. This doesn't mean the photon travels backward in time. It means the question which path did it take has no physical content until you define the measurement. Heisenberg once said when asked a similar question, there is no phenomenon until we record it. I put it more crudely. Nature doesn't show you behind the scenes. It only brings you on stage when the curtain is already up. In modern double-slit experiments, if you don't measure the path, the wave function spreads through both slits, not like a real cloud, but like a probability structure. If you measure, you force the system to pick one of the possibilities that previously coexisted. If you don't measure, there is no such thing as the photon is secretly going through the left slit, and no such thing as it goes through both slits but hides it from me. No measurement, no path. What exists is only the wave function. From 1999 to 2020, Interference experiments with large molecules from C60 to 2000 mu molecules in Marcus Arndt's group all show the same. Possibility exists when unmeasured. Outcome exists when measured, but what happens in between is not a valid question. I like to joke with students. If you ask the universe something it doesn't define, the universe will answer by ruining what you're trying to observe. Actually, nothing gets ruined. You're just asking beyond the scope of concepts nature accepts. So when you ask, what does light do when no one is looking? The most honest answer is, it doesn't do anything in the sense you want to assign. Only the wave function exists, a probability structure waiting for interaction. No story, no path, no journey, only possibility. And when measurement happens, possibility becomes event. After going through enough quantum twists, photons taking every path, wave functions collapsing on measurement, interference vanishing. When you look, it's time to pause and straighten out the things no one in the physics community argues about. This is the part I call the reality check. Pieces of truth that have been verified millions of times in hundreds of kinds of experiments all over the world for more than a century. The first thing that's non-negotiable. Light in vacuum always propagates at speed c, exactly 299,79792,458 mon/. The number fixed in 1983 when the international community decided to redefine the meter based on the speed of light itself. That speed doesn't change whether you're at rest or running, whether the light source is moving or stationary, whether the whole galaxy is rotating around the Milky Way center at 220 kilometers/stars. More than a century of experiments from Michelson and Morley, 1887, Kennedy Thorndike, 1932, to modern atomic clock tests at NIST, 2015. All give one single answer. C is an absolute constant. The second, photons have zero rest mass. Precision experiments measuring the decay of electromagnetic fields from Davison Germer, 1927, to recent astronomical measurements by ESA via radio wave polarization spectra, 2010-2020, set the photon mass limit below 10 μh, EFD squared essentially zero. The third, light arrives in discrete packets, photons. This is no longer Einstein's 1905 theory. It's technological fact. In modern labs in Vienna, MIT, NIST, people generate single photons via SPDC, spontaneous parametric down conversion, and count each one with superconducting detectors at near 90% efficiency. Each photon produces exactly one click, never half a click, never spillover. That's direct evidence of light's discrete nature. The fourth, if you don't observe the photon's path, it produces interference, the fringe pattern. From Young's 1801 experiment to modern single photon source experiments by Aspect 1980s, Grangier 1986, Zeilinger 1999-2020, you always get the same conclusion. Multiple possibilities coexist and interfere. Interference isn't magic. It's the inevitable consequence of the wave function spreading across space. The fifth, equally important, when you observe the path when you ask the photon which slit it went through, the interference pattern disappears and the photon behaves like a classical particle. This result has been repeated thousands of times in every context. Photons, electrons, neutrons, helium atoms, C60 molecules, 2000 mu molecules all behave the same way. Wheeler's delayed choice experiment, proposed 1978, performed 2007 and 2014, even shows you can decide the photon's behavior after it has passed the slits, confirming that the concept of a real path doesn't exist before measurement. The sixth, the path integral accurately describes every experiment we've ever done involving light and electrons. I developed the first version of it in 1947, then expanded it in 1948 in the report at Shelter Island. From then to now, the path integral has become the foundation for QED quantum electrodynamics, the theory Schwinger, Tomonaga, and I developed and shared the Nobel for in 1965. QED is the most accurate theory in the entire history of science. Want to know what most accurate means? The anomalous magnetic moment of the electron G2 is predicted by QED to 10 nubic squared accuracy, 1 part in a trillion. Experimental result from Harvard in 2006, Gabriel's group, and ultra-precise measurements in Colorado in 2020 match the theory so closely you have to look at the 12th decimal place to see any difference. No theory humans have ever written Newtonian mechanics, relativity, fluid mechanics, thermodynamics achieves this precision. QED does. The path integral is at its core. The seventh, all of the above hold in every experiment ever performed at every energy level, from a few eV to a few GV, from darkroom experiments in Paris in 1986 to SLAC accelerators in 1997, from lab interferometers to cosmic signals from quasars 10 billion light years away. No exceptions. That's why when I sum all this up for students, I say, you don't need to understand what light is to do physics. You just need to know what nature definitely does. So here's the reality check. Light always travels at speed sand. Photons have zero rest mass. Light arrives in discrete energy packets. It produces interference when not measured. It appears as a particle when measured. The path integral describes all these phenomena with the highest accuracy science has ever achieved. That's not belief, not philosophy. That's data from more than 120 years of experiments, from 1905 to 2025. Nature is speaking very clearly. These are the things I do, whether you like it or not. After listing the things we truly know, it's time to remove from our heads the things that modern science has completely rejected, not because of philosophy, but because experiments have slapped us right in the face with the facts. The first thing you should no longer believe: the ether does not exist. The idea of the ether dominated the 19th century, appearing in every textbook from Britain to Germany, until Michelson and Morley in 1887 measured the speed of light in every direction and found nothing, not a little signal. Zero. Kennedy Thorndike, Ives Stilwell, and then modern laser experiments at NIST all repeated the result. There is no medium that Earth moves through that affects the speed of light. Every version of the ether stationary dragged along with Earth died in the lab. The second thing you should no longer believe: there is no real path of the photon. I'm not saying this to shock you. This is what experiments have repeated thousands of times. In the double slit experiment, if you don't place a detector, the photon creates an interference pattern, something that can only happen if it doesn't go through a single slit. But when you place the detector to ask the photon where it went, the interference pattern disappears and you only see two particle-like bright bands. There is no way to assign a real path to the photon without contradicting the data. Wheeler, in his 1978 delayed choice experiment, even showed that your decision to ask the photon or not made after it has already passed the slit still affects the outcome. If the photon had a real path fixed in advance, this experiment would have given different results. But it didn't. Nature says there is no real path. The third thing you should no longer believe: light does not have a fixed essence of being wave or particle. These words are just poor human descriptions based on classical experience. A wave is what you see on the surface of water. A particle is something you can hold in your hand. The photon is like neither. It produces an interference pattern like a wave when not measured, and appears as a particle when measured. Electrons do the same. Neutrons do the same. C60 molecules do the same. From 1999 to 2020, Arndt's group in Vienna sent giant molecules flying through gratings and produced interference. An object over 7,000 mu still is a wave. But if you attach a detector to track it, the interference pattern disappears. It is a particle. Wave and particle are no longer essences. They are measurement outcomes. The fourth thing you should no longer believe: there is no coherent story that takes place between the emission and absorption of a photon. This is humanity's biggest intuitive mistake. We keep thinking there must be a real journey the photon travels. But the wave function does not describe a journey. It describes possibilities. The path integral does not describe paths. It describes the sum over all paths. When you don't measure, there is no story. When you measure, the story you see is only the final outcome. the point where the photon appears. There is no hidden process, no travelogue, no implicit trajectory lurking in the background of reality. There have been hundreds of attempts from the 1930s to now to construct alternative microscopic stories, from Bohmian mechanics to hidden variables, from de Broglie's pilot wave to objective collapse theories like GRW. None of them reproduce all the data of QED with the 10^10^2 precision that experiments demand. All fail somewhere, not because they are crude, but because nature does not contain any classical story to reconstruct. Finally, the most important thing you should no longer believe: there is no hidden essence behind every phenomenon. I know this makes many people uncomfortable. Humans like to think there is a real reality behind every measurement, a secret set of rules, an invisible mechanism. But more than 100 years of experiments show only one standard. Does the prediction match the data? QED matches to 12 decimal places. Interferometry matches. Compton scattering matches. The Lamb shift matches. The 2s2p energy level shift in hydrogen matches. Theory with errors smaller than 10 thermomecu. No Hibben theory achieves that accuracy. When I say there is no hidden essence, I'm not saying the universe has no structure. I'm saying that structure is not in the form of a classical story that the human mind likes to construct. Nature doesn't write autobiographies. Nature only writes equations. What we know is what we measure. What we measure is what the wave function and path integral predict accurately. The rest of the things we thought must exist are just leftovers from intuition fooled by the macroscopic world. My second reality check is that simple. Discard the old beliefs, not because of philosophy, but because the data has redrawn the map of reality. More than once in my life, I've had to repeat a sentence I believe is one of the greatest truths in science. Nature can't be fooled. Nature isn't fooled by your desires, hopes, or beliefs. It just does exactly what it does, whether you like it or not. I said that sentence most forcefully in 1986, when the Rogers Commission investigating the Challenger space shuttle disaster asked me to participate. Many people in the space program wanted to believe the O-ring could withstand lower temperatures than designed. But desire doesn't change reality. When I dunked the O-ring sample into a glass of ice water and squeezed it in front of the live televised world, I just wanted to say one thing. Nature doesn't care about launch schedules, budgets, or political pressure. It only obeys its own laws. When humans try to fool it, it responds with truth, sometimes very cruelly. I tell the Challenger story, not to change the subject, but to say that light behaves under exactly the same principle. You can want the photon to have a real path. You can want the universe to be reasonable by your intuitive standards. You can want to believe the microscopic world follows familiar logic like marbles, like water waves. But nature never signed a contract with your intuition. If experiments say the photon has no path, then it has no path. If interference disappears when you observe, then that's what happens. Not because the photon likes to trick you, but because measurement is a real quantum interaction. If the wave function only describes possibilities instead of a hidden reality behind, then that's how nature operates. You can get angry about it, but nature doesn't change just because you feel uncomfortable. Directness is what I've always loved in physics. It forces you to face the truth, even when the truth keeps you awake at night. When I say the photon takes every path at once, students ask, how can that be possible? I answer, the right question isn't, does it seem reasonable, but does the data say so? The entire path integral, the entire QED, all the measurements accurate to 12 decimal places point to one answer. Nature doesn't care about the pretty pictures your human brain is used to using. It doesn't operate by your intuition. Your intuition comes from the macroscopic world where friction exists. Gravity is weak. Speeds are slow. The quantum world isn't like that. It doesn't need to be. Every time I stand in front of a blackboard lecturing Caltech students, I always remind them, science is not a journey to find explanations that make you comfortable. It is a journey to confront what nature actually does, even when that shatters what you thought you knew. Light with its non-existent path, with interference appearing only when you're not looking, with particle behavior popping out one by one, is the clearest proof. It doesn't care if you want the world to be logical. It only cares about truth. For me, this isn't scary. It's beautiful, because when you accept that nature has no obligation to meet your desires, you stop trying to fool it. Stop imposing wrong metaphors on it. Stop forcing it to resemble what it isn't. Only then do you truly begin to understand physics. Understanding light in the end is not just understanding a physical phenomenon. It is understanding how the human brain constructs its own intuition, and how that intuition fails completely when stepping into the microscopic world. That's why I always tell students that studying light is like walking into a room full of mirrors. You think you're looking at the universe, but really you're looking at the limits of your own perception reflected back at you. Take history as an example. Newton, in 1704, believed light was particles, not because he was ignorant, but because the intuition of someone living in a world of marbles, bullets, and falling apples made it seem that way. He argued with logic that anyone would find reasonable. Then Young, in 1801, simply did a simple double-slit experiment, and the entire particle model collapsed. Light interferes. No particle does that. So, generations of scientists after Fresnel, Fraunhofer, Maxwell built a universe where light is a wave. Then Maxwell in the 1860s gave us electromagnetic equations so beautiful that everyone thought, that's it, we understand light. But no, Einstein in 1905 appeared and said, sorry, but light comes in packets. The whole world got slapped awake again. Wave? No way, particles. Then the next generation born. Schrödinger. Heisenberg in the 1920s had to throw away that intuition too, and accept something that was both wave-like, particle-like, and neither, the wave function. Then it was my turn, and people like Schrödinger, Tominaga in the 1940s, to abandon the picture of the electron following one trajectory and replace it with the path integral, where electrons and photons don't follow any path but every path. Each generation has to smash the intuition of the previous one to build a new one. And the wonderful thing is, every time intuition is broken, we get closer to the truth. That's how knowledge works. It never goes from one certainty to another. It goes from comfort to discomfort to temporary truth, then to new discomfort. Light is the window opening onto that entire journey. It forces us to accept things we don't like. It forces us to question how we see the world. And if you're American, a culture that loves confidence, loves saying, I know, loves standing tall and declaring, this is how the world works, then light is the best lesson. Don't trust your own intuition if the data doesn't support it. Imagine you're holding a flashlight in your hand. You turn it on and the light shoots across the room. You see it go straight, reflect at the right angle, pass through glass according to Snell's law. Everything looks neat, logical, beautiful, like something designed by an American engineer in Silicon Valley. But that's an illusion. That's the simplified version nature leaves after canceling infinite possibilities. You don't see the chaos. You don't see the superposition. You don't see the infinite parts crossed out. You only see the final product, the version rendered from the quantum foundation. Learning about light means understanding that the simplicity you observe is not the foundational reality. It is only the version humans can see. This doesn't just apply to photons, it applies to you. Your brain also works by canceling infinite possibilities and leaving only one simple story you believe is real. But psychological reality is as complex as quantum reality. You don't see the entire process. You only see the familiar outcome. When you think you understand someone else, you're really reading a filtered version, not the original. When you think you know your own emotions, you're looking at the final render, not the mess underneath. Light teaches us a lesson in humility. Human intuition is a good tool in the slow macroscopic world, but it was never born to understand how the world really operates at the deepest level. And that's why physics matters. It saves us from our own prejudices by forcing us to confront data, not the stories we like to tell. Every time a scientific generation steps onto the stage, nature smiles and says, you were wrong. But don't worry, you'll do better. Understanding light helps us realize something far deeper. The most beautiful thing in science is not the answers we already have. But the gaps, the dark regions, that even after we've illuminated them with the full power of human intellect, still refuse to light up. Some people see this as failure. I don't. I think that's exactly how science works, like the self-correcting mechanism of curiosity. Every time we solve one mystery, the universe doesn't close the door. It opens 10 more deeper, darker, more complex. Light is the perfect example of this. When Newton described light as particles, he thought he'd finished the story. When Young showed interference, people thought, so light is a wave. When Maxwell showed electromagnetic waves propagating in vacuum, the world thought, Feynman, and we understand. Then Einstein said light comes in packets. Then the 1920s, the wave function forced everyone to rewrite the very definition of reality. Then QED, where light takes every path at once. Not one, not two, but every path. It seemed like the story was done, but no. New questions arise. How does the wave function collapse? What determines the boundary between quantum and classical? How does the photon exist before we measure? Is there a deeper theory beneath QED? Why does the fine structure constant Is have the value 1137.03599? Why did the universe pick exactly this set of laws instead of another? The Maxwell equations, the Schrödinger equation, the Dirac equation, the past integral all work with insane accuracy, but none answers the most important question. Why are they true? They're true because they're true. That's the best explanation we have. I always think this is funny in an endearing way. We live in a universe of perfectly working equations, but we don't know why they exist. This doesn't keep me awake. It makes science more beautiful to me. Look at light. We know the photon has no real path. We know the microstate of the probability wave can't be observed. We know interference appears when unmeasured, disappears when measured. We know the speed of light is always c, no matter how fast you chase it. We know the path integral predicts everything to 12 decimal places. But we don't know what the photon is in an essential sense. We don't know why nature operates with complex mathematics. We don't know the deep meaning of collapse. We don't know why observation changes the system's behavior. We don't know whether time means anything to the photon beyond the equation saying zero proper time. We have descriptions, beautiful, accurate, powerful, but no complete story. Anyone who claims they understand light in a comprehensive sense is either joking with you or doesn't understand what they're saying. You can calculate everything about light with crazy precision: wavelength, dispersion, scattering, polarization, synchrotron radiation from electrons orbiting at 99.99999% the speed of light in accelerators. You can predict the hydrogen energy level shift to 11 decimal places. You can solve every classical optics problem with Maxwell's equations. But if I ask you, what is the photon doing between the moment of emission and absorption? You can't answer. Not because you're not smart, but because nature didn't include that answer in the data sheet. That's a gap. If I ask, is the wave function real? Does it exist in space or just on paper? You can't answer. If I ask, why does observation make interference disappear? You can offer decoherence models, but you still haven't touched the essence of observation. If I ask, is there a theory deeper than QED? The standard model currently says maybe, and experiments say not yet. These gaps don't make physics weaker, they make it stronger. Because when you look into the gaps, you're seeing where human intelligence can expand. Remember, every scientific revolution began from a gap that someone was curious enough to stare into. Newton looked into the gap between planetary orbits and falling apples. Maxwell looked into the gap between electricity and magnetism. Einstein looked into the gap between ether and the speed of light. Fermi looked into the gap between beta decay and missing energy. And I looked into the gap between particle description and wave description. And the path integral jumped out. Science doesn't advance by believing in what we already know. It advances by looking at what we don't know and not being afraid of it. With light, the deeper we understand, the more we find ourselves standing in fog. But that's not failure. It's an invitation. It's a map with blank regions yet to be drawn. It's a reminder that our intelligence is never finished and never will be. Americans love clarity, love quick solutions, love definitive answers. But science, especially quantum physics, doesn't work that way. It doesn't hand you neat endings. It gives you curves, holes, cracks, unfinished questions. And to be a real scientist, you have to love those gaps too. When you read the news and hear a scientist say, "We don't know yet," don't see it as weakness. See it as the most beautiful honesty human intelligence can achieve. When you study light and see questions without answers, like the true nature of the wave function, the meaning of measurement, or the real shape of the photon, don't be disappointed. Smile, because you're standing exactly where every great discovery in history began. Light doesn't give you a complete story. It gives you infinite depth. The more you understand, the more you realize you don't know. That isn't just normal. It's the most beautiful thing in science. Reaching the end of this journey, when looking back, the clearest thing is not that we understand light, but that we have learned a better way to approach truth. From the seemingly obvious question, how does light move, to the discovery that nothing really moves, in the classical sense only, the enthusiasm of electromagnetic fields, of competing amplitudes in the path integral. All of it forces us to leave behind the crutches of intuition we once thought were knowledge. You've walked with me through Huygens and Fresnel, through the century when ether was considered the foundation of the universe, through the shock of Michelson and Morley in 1887 that shook the world's belief. Then you saw Maxwell step in and give us a universe woven from self-sustaining electric and magnetic fields. Then Einstein in 1905 bent the entire concept of time and space just because of one simple principle. The speed of light is the same for everyone. Then quantum Hertz, Leonard, Einstein of the photoelectric effect forced us to see light as packets of energy. Then the double slit experiment threw all intuition against the wall when the photon behaves like a wave when not measured and like a particle when measured. Then the wave function and complex probabilities forced us to accept that nature doesn't tell stories, it only computes. Then the path integral showed that light, electrons, everything tries every path and self-cancels to produce the single result we see. Then QED proved this theory accurate to absurd levels, 1 part in 10 mach squared A level. No other theory in history is touched. Then the reality check taught us that there are things we truly know. Photons have no rest mass. Light arrives in packets. Interference disappears on observation. C is absolute, and things we are no longer allowed to believe. Either real paths, wave or particle essence, coherent stories behind measurements. Then we reached the bigger conclusion. Nature has no obligation to conform to your desires. It doesn't become simple because you want it simple. It doesn't provide a story because you want a story. It isn't impressed by your confidence or concern. It only obeys its own laws. And right here, at the end of every layer of abstraction, we see what science really is. A method, not a set of answers. You observe. You doubt what you just observed. You build a model. Then you test it. If the model is wrong, you throw it out. If it's right, you keep it. But only temporarily, until stronger data demands you discard it. Every physics revolution began with the willingness to say, maybe I'm wrong. Newton was right in his domain, then wrong at high speeds. Maxwell was right in his domain, then insufficient when quantum appeared. The wave picture was right in its domain, then wrong when we fired photons one by one. The particle intuition was right in some cases, then wrong when interference appeared, even without any material wave vibrating. The classical path model was right as an approximation. Then the path integral said, no, you have to sum over infinite paths. If science is a journey toward truth, then this truth is always temporary, always waiting for a new experiment to smash it. The only thing enduring is not the conclusion, but the method. Observe, doubt, model, verify. The American way of saying trust but verify becomes, in science, verify or throw it out. What makes me love physics is not the answers, but the absolute honesty it forces people to have. If you try to fool it, it will confuse you. If you try to ignore it, it will come back in the next experiment. If you try to force the universe into your desired mold, it will answer with results that make you throw the mold away. The journey through light we've just taken is the perfect illustration of this. Each new layer of understanding doesn't reinforce our confidence. It exposes how shallow what we thought was obvious really is. Light moves without anything moving. Light goes straight but tries every path. Light is a particle but interferes like a wave. Light has no real path but appears exactly where a mathematical model predicts. The more you understand it, the more you see you don't understand. But that's the beauty. I've said this many times to students. If you're not confused, you don't understand the problem. Confusion isn't a sign of failure. It's a sign you're standing right where knowledge is about to expand, and the universe loves putting us in that position. Einstein once wrote that the most amazing thing about the universe is that it is comprehensible. I agree, but I always add, the second most amazing thing is that every time we think we've understood, the universe says, no, that's shallow, look again. So when I sum up this entire journey, I don't say you now understand light. I say you understand, in a more honest way, the truth that light doesn't fit your intuition, and your task is to keep up with it, not force it to fit you. You understand that gaps aren't failures, they're invitations. You understand that doubt doesn't kill science, it feeds science. You understand that every model is just a temporary bridge over deep water, and one day you will have to tear down the bridge to build a new one. And finally, you understand what I've believed since the first day I held chalk in front of a class. Science doesn't teach you to believe in anything. It teaches you not to believe in anything until the data forces you to. Light isn't the simple thing you see. It is an entire lesson in how the universe operates and how human intelligence must adapt to keep up with it. Don't confuse confidence with truth. Truth doesn't care about how confident you are. It only cares about how honest you are. This journey wasn't meant to make you comfortable, but to make you awake to the power of data, of doubt, of the willingness to discard intuition when it blocks truth. So if after 20 parts you feel smaller in the face of light, congratulations, that was the goal. Science doesn't make you bigger than the universe. It gives you the chance to see how vast the universe is, so your intelligence must keep expanding to match. And to end this journey, I just want to ask you one question. One single question. I hope will follow you longer than the speed of light. If light can travel without ever moving, what else are you still sure about in this universe? If you find this journey has awakened your curiosity enough, please hit subscribe so you don't miss the next discoveries. See you in the next adventure where the universe continues to challenge everything you thought you knew.